Next, we're going to look at how to factor the sum and difference of cubes. Now let's recall we have a formula for factoring a difference of squares. If we have a binomial and each term is a perfect square, where we're also taking a difference, we can factor this into the sum and difference of the things getting squared. We also are able to factor a sum of two cubes and a difference of two cubes, and we have formulas for both of these. Let's take a look at the formulas and a couple of examples. First, we'll look at the sum of cubes. So if we have a perfect cube plus another perfect cube, we can factor this into two factors. The first is the sum of the two quantities being cubed, which looks just like the difference of squares started off. But then the second factor is a little bit more involved. It's going to be that first term squared minus the product of those two terms plus the last term squared. So for example, if we have x cubed plus 27, we can recognize this as the sum of two cubes because x cubed is x cubed and 27 is 3 cubed. So then when we go to factor it, we've got x plus 3. We take the sum of those two quantities, and then we've got to take the first one squared, so that's going to be x squared, minus the product of those two. X times 3 is 3x, so we have minus 3x, and then plus the last one squared. 3 squared is 9. And so the factorization is x plus 3 times the quantity x squared minus 3x plus 9. Now, theoretically, it might be possible to use the unfoiling method or the AC method or trial and check, depending on what the coefficient is here. But we know that we can sometimes factor trinomials even further. But when we're dealing with a sum or difference of cubes, if there's no greatest common factor or something else in the beginning, then once we've used the formula, this trinomial generally cannot be broken down any further. So this ends up being our final answer. That's the sum of cubes. We have a similar formula for the difference of cubes. So let's take a look at that and we'll do an example. Here, if we have f cubed minus l cubed, we can factor this. And the formula is very simple, but just a little bit different. We're going to start off with f minus l, which you can remember because we've got a minus here. And then for the sum, we've got a sum, and so plus plus minus minus. And then for the second factor, it's going to be f squared plus fl plus l squared. So it's really identical to the formula for the sum of cubes, except the location of the subtraction has changed. But otherwise, it looks pretty much identical. So let's look at an example of factoring a difference of cubes. Let's take a look at 8a cubed minus 125b to the 6th. So here, 8a cubed is a perfect cube. It's the quantity 2a cubed. 2a times 2a times 2a is 8a cubed. And then 125b to the 6th is 5b squared, quantity cubed. And it is a difference, so we can use this formula for the difference of cubes. So first, we've got f minus l, so that's going to be 2a minus 5b squared. Then times f squared. Now 2a, quantity squared, is going to be 4a squared, plus the product of those two terms. 2a times 5b squared is 10ab squared, plus the last term squared. If we take 5b squared and square that, we get 25b to the fourth. And so this is our factorization. Anytime we have a sum of two cubes or a difference of two cubes, we can use these formulas to factor those polynomials. And if you want to derive these formulas yourself, what you can do is you can actually calculate the products on the right-hand sides and look to see that most of the terms end up canceling out, and you're just left with two terms, either f cubed plus l cubed or f cubed minus l cubed.